Everyone, welcome to the next quantum computing meetup that is organized by quantum computing groups from Washington, D.C., Toronto, and Warsaw. My name is Pavel. I will be a moderator today. I'm the CEO of Quantum AI Foundation and organizer of the Warsaw Quantum Computing Group meetup. And today we have pleasure to host our great speaker, Professor Dr.Niu from University of Central Florida. And as you can see, she will give a talk titled Towards Resource Efficient Quantum Computation, Dynamic Circuit Compilation and Optimized Observable Estimation. So looks very interesting. Before we start, just a few announcements. So first of all, as you can see, this meeting is recorded, and later the video will be available on our YouTube channel. So actually there is an live streaming on YouTube as well. And we've also agreed with CUM that this meeting can be interactive. So if you have any questions, you can raise your hand and we'll try to interrupt to just allow you ask your question directly. Alternatively, if it's not urgent, you can also post your question on the chat, and there will be a Q&A session at the end anyway. So if there are some urgent questions, you can just raise your hand. And finally, we would like to announce our next event. So next week on Sunday, Dr. Kunal Das will give a talk about a PSO-inspired global neighborhood-based qubit mapping. And then on August 16, Dr. Bruna Shinohara will tell about quantum on the flip side, a global south perspective on quantum hype. Then August 23rd, Terry Bollinger, who is with us today as well, will tell us about the strategies for non-qubit quantum computing. And later on September 6th, Lydell Aron will tell us about factoring with waves, a frequency phase perspective on quantum computation. And later on September 13, another talk will be given by Terry Bollinger. It will be a critical look at infinitesimals in physics. And on September 21st, Dr. Anirban Mukerjee will tell about tensor factorized Hamiltonian downfolding to optimize the scaling complexity of the electronic correlations problem on classical quantum computers. And October 4th, Dr. Jarek Duda from Jagiellonian University will tell us about the maximal entropy random walk as corrected diffusion in agreement with quantum predictions. And October 11th, another talk given by Terry, how to win $1 million math prize. So finally, we'd like to thank our sponsors for supporting us and helping us in organizing and advertising the event. And yeah, that's all from my side. So I will now stop sharing my slides. And C1, if you are ready, I think we can start. So first of all, thank you for accepting our invitation to give this talk. And if you're ready, the Zoom is yours and you can start sharing your slides.
Sounds great. Thank you. Thanks for the nice introduction. And also thanks for inviting me again to present my new works. In this talk, I will present two of my recent works about dynamic circuit compilation and optimized observable estimation. First, my focus is I will talk about this dynamic circuit synthesis for resource optimization. Before I start, I want to acknowledge all my collaborators. This work is finished during my stay as a postdoc at Lawrence Berkeley National Lab. All my collaborators are amazing folks from Lawrence Berkeley National Lab and UC Berkeley. So first, let me briefly introduce dynamic circuits. Dynamic circuits is a type of special circuit that include mid-circuit measurement and feed-forward operation. This figure shows an example of a simple dynamic circuit. We have two qubits, Q0 and Q1. We measure Q0 in the middle, and then we store the measurement result in this classical register. If the measurement result is Q1, we apply hot mark gate to Q1, and if the measurement result is 0, we apply X gate to Q1. Because of this mid-circuit measurement and feed-forward operation, we call it a dynamic circuit. It was originally proposed for quantum error correction for syndrome measurement, but recently it has demonstrated lots of benefits in terms of quantum resource optimization. By that, I mean dynamic circuit can reduce circuit depth and number of CNOTs. Here is an example of using dynamic circuit for preparing constant depth GHZ state. If we prepare a GHZ state using a unitary circuit, we can see as we increase the number of GHZs, increase the size of the GHZ state, we need more and more CNOS to prepare this state. But if we use dynamic circuit, we can prepare an arbitrary GHZ state with constant depth. And this part is the dynamic circuit. The second example is this long-range CNOT gate. If we want to implement a long-range CNOT gate, this is the control qubit and this is the target qubit. As we increase the distance between the control and target qubit, if the target topology is a linear topology, we need to insert more and more swap gates to make sure that we can achieve this long-range CNOT gate. So the circuit depth will grow linearly as we increase the distance between the control and target qubit. But if we use dynamic circuit, we can achieve this long-range CNOT gate in constant depth. Apart from this GHZ state and long-range CNOT gate, dynamic circuits also have applications in like quantum Fourier transformation, quantum phase estimation, and quantum teleportation. All of these methods, they are based on dynamic circuits that are constructed manually. There is no method that can generate a dynamic circuit for arbitrary state or unitary operator. That motivates us to ask the question, how do we automatically generate dynamic circuits for arbitrary states or unitary operators? In our paper, we proposed a tool that can do this task. But before I introduce our method, first I want to introduce the concept of circuit instantiation, because it's a key component in our method for dynamic circuit. Let's say we have a parameterized quantum circuit. If we now we want to find the optimal parameters such that this parameterized circuit can implement a target unitary V. We can think about instantiation like a process of optimization problem. Now we want to find the optimal parameters to optimize 1 minus trace of V dagger C alpha, where V is our target unitary and C alpha is the unitary of the parameterized circuit. We want to find the optimal parameters of alpha for our cost function using instantiation. Instantiation is the core of the bottom-up synthesis. For a unitary, like this is a 8x8 unitary matrix, we want to find a circuit, that 3-qubit circuit that implement this unitary. This is called unitary synthesis. We can use instantiation to help with the unitary synthesis. This is the workflow. So first we create an initial circuit. It is a parameterized circuit. Then we use instantiation to optimize the parameters. If the error is not acceptable, we need to extend the circuit template by adding some other parameterized layers, and we do the instantiation again to optimize the parameters. We repeat this process until the error is acceptable, then we obtain our synthesized circuit that can implement our target unitary matrix. So we can see the instantiation plays a key role here in this bottom-up synthesis process. One well-known method for this bottom-up synthesis is called Q-search, which is first proposed by this paper here. This is the framework. First, we initialize the circuit using a layer of U3 gates. Then we use instantiation to optimize the parameters. If the error is not acceptable, we add another layer which contains a 2-qubit gate and 2 U3 gates. We add this layer to different qubit pairs which are physically connected if we give a hardware topology to the circuit. And then we expand the searching process and use instantiation to optimize the parameters. We iteratively add more layers until we find the optimal circuits that can implement the target unitary. Apart from this unitary synthesis, instantiation also is very helpful for circuit transformation. By circuit transformation, we mean it can optimize the quantum circuits or modify the quantum circuits. So let's say we have an initial circuit, we can reduce or change the circuit template and we re-instantiate the quantum circuit. If the error is acceptable, we obtain an optimized circuit that can also implement the target unitary matrix with less number of gates. So now I will give some concrete example of how to use instantiation for circuit optimization. First is the gate deletion. We have a circuit template that can implement the target unitary, and then we try to remove a gate. We remove one U3 gate here. We instantiate the circuit again. Now we change the color because we obtained a bunch of new parameters that can. This parameters is different from this blue one. We can check if this new circuit is acceptable when the error is low enough. If it is not, we reject this new circuit and then we change the template again. We repeat this process such that we can until we find a circuit that with less number of gates. In such a way, we can optimize the circuits with less number of gates. The second one is to do circuit retargeting. So for example, our initial circuit, the basis 2-qubit gate is C0 gate. We can just use instantiation to transform it to another basis gate with, for example, the ZZ gate using instantiation very easily. So that's it for this introduction for instantiation. Now I will show how we use instantiation for dynamic circuit generation. In our paper, we proposed methods to use automated instantiation to generate dynamic circuits for state preparation and unitary preparation. This figure shows our protocol. We have S system qubits and one ancillary qubit. Here we set the number of ancillary qubit to 1 just for illustration, but later we will show how we can extend these ancillary qubits to arbitrary number. For state preparation, we initialize all the qubits to state 0, and for unitary preparation, the system qubits can start from arbitrary states, but the ancillary qubits still need to start from state 0. First, we apply a parameterized unitary UB to all the qubits. Then we measure the ancillary qubit. If the measurement result is 0, we apply U0 to the system qubits. If the measurement result is 1, we apply U1 to the system qubits. The goal is to find the parameters in UB, U0, and U1 such that we can prepare the target state or unitary only on the system qubits. For this parameterized unitaries, UB, U0, and U1, we can think about it as a parameterized quantum circuit. Now we want to find the optimal parameters for this circuit to implement the target state or unitary. Now the challenge is that we have some non-unitary operations, which is this mid-circuit measurement and feed-forward operator. How to deal with these non-unitary operations in the instantiation is a big challenge. We need to propose new cost functions for instantiation for these non-unitary operators. So first, let me introduce our cost function for dynamic state preparation. This is the protocol for state preparation. This is an example when we have two ancillary qubits. When we have two ancillary qubits, we measure them and we will get 2 to the power of 2, which is 4 measurement results corresponding to 0, 0, 0, 1, 1, 0, and 1, 1. And this is the cost function. Suppose we have A ancillary qubits, we will obtain 2 to the power of A output states because we will have 2 to the power of A measurement results. For each output state, we call it a phi I, it needs to approximate T, which is our target state, tensors I. This I corresponds to the measurement result of the ancillary qubits. So this is the intuition of our cost function for state preparation. For this phi I, it is equal to this 0 on all the qubits, and then we apply a UB to all the qubits, and then here is UI, tensors outer product of I. UI is the unitary on the system qubits, and this outer product of I is the measurement results on the ancillary qubits. But now we only have this cost function for instantiation. We still need to think about how do we really construct the circuit for this UB, U0, and U1. So now let me introduce our synthesis framework. First one is called DC-Q search. So we borrow the framework from Q search. Here for each circuit template, we just replace each circuit by a dynamic circuit and use our cost function for instantiation to check if this circuit can prepare the target state. But this has a scalability limitation. We can see the searching space grows exponentially, so it can only work for circuits that has less than 6 qubits. To scale it up, we propose another method called DC-instantiation. During the we first tried some example using this DC-Q search, and we found that there are some patterns in the circuit generation. The obtained circuit usually is constructed of alternating layers, and then the circuit depth grows logarithmically. So based on these patterns, now we decided that for large circuits, we do not do this searching process. We just construct the circuit template based on the pattern observation and use instantiation to check if this circuit structure can prepare the target state. And this, we call it DC-instantiation. It can scale this process to like 11, 12 qubits. Here are some results. First, we show the results of state preparation for GHZ state with only one ancillary qubit. So this is the GHZ state, which is the superposition of bunch of state 0 and state 1. We prepare here the circuit structure for GHZ state from 4 to 8. Let's take a look of this GHZ4. This A represents an ancillary qubit. This structure only shows the circuit structure for UB. Just to recap, UB is this part. We will apply circuit measurement to the ancillary qubit, and after that is the feed-forward layer. For simplicity, we limit the feed-forward layer to one layer of U3 gates. So we just remove that part and only show the circuit structure of UB. For each block, it is one CNOT gate with two U3 gates. We can see there is a clear pattern when we try to generate this circuit structure. Here are some results. We compare this GHZ state prepared using dynamic circuit with unitary circuit. We can see in terms of CNOT gates, the number of CNOT gates is increased, but in terms of circuit depth, dynamic circuit achieves shorter circuit depth compared with unitary circuits. If we introduce more ancillas in the dynamic circuits, we can further reduce the circuit depth. You will find more results in our paper. Here are the results for preparing W states and decay states with one ancilla. This is a W state, and this is the decay state. We can see also dynamic circuits can sometimes increase the number of CNOT gates, but the circuit depth is always reduced. Now we have our states prepared by dynamic circuits. We want to evaluate these states on quantum hardware. So first, we check some simple and small circuits on AQT quantum hardware. AQT stands for Advanced Quantum Test Bed. It is a superconducting quantum hardware owned by Berkeley Lab and UC Berkeley. We run two circuits, GC4 and W3 on AQT machine. Here's the results. The x-axis is the bit strings and y-axis is the counts. We can see for GC state, the highest frequency of the counts is 0000 and 1111, which is the correct state for GC state. For W3, the highest account probability of the counts is 001, 010, and 100, which is also the correct state for W3. This can give us the confidence that the circuits that we generated using dynamic circuits can really prepare the target states that we want. So now we show more results on IBM quantum hardware. The x-axis is a bunch of quantum circuits, and the y-axis is the TVD, which stands for total variation distance. So it calculates the distance between the ideal distribution and the distribution, the noisy distribution. So the lower is the better. If there is no error, TVD will be 0 for all the circuits. We can see comparing dynamic circuits with unitary circuits, dynamic circuits has shorter circuit depth, but the TVD is always higher, most of the time is higher than the unitary circuits. And here is the results on IBM quantum hardware. We first run them without any error mitigation methods. Then we add staggered dynamical decoupling to the circuits to reduce some decoherence error. We can see this staggered dynamical decoupling can reduce this TVD, but in general, this dynamic circuits has worse fidelity results compared with the unitary circuits. It is not surprising because dynamic circuits in this case, it slightly increase the number of CNOTs. And also mid-circuit measurement, it has more errors compared with CNOT gates. So it's not surprising that dynamic circuits cannot perform as good as unitary circuits. Now I will introduce our cost function for dynamic unitary instantiation. If we have a unitary circuit, we can use this Hilbert-Schmidt distance as the cost function for instantiation. But now we have this mid-circuit measurement and feed-forward loop. So what we can do is that according to deferred measurement, we can move this classical control unitary before this measurement to construct a big U operator. We want to prepare the target unitary V on the system qubits, but the ancilla qubits can end up with arbitrary states. So we give a W operator here to give more freedom on the ancilla qubits. Now we want this big U operator approximates V tensors W. Another constraint we have is that the ancilla qubits has to start from state 0. So we apply a F0 here. So it is composed of identity on the system qubits and outer product of 0 on the system qubits, on the ancilla qubits to make sure that ancilla qubits start from state 0. We can see if we do not have any ancilla qubits, this cost function is exactly the same as the Hilbert-Schmidt distance cost function. We further analyze our cost function and then we find that actually we can remove this W operator. So we proposed our second cost function. To understand it, we can check the representation here. This big U operator can be represented by the tensor product between ancillar qubits and system qubits. Since we only care about the ancillar qubit when the initial state is 0, so actually for this big U operator, we only care this U00 and U01. So we want this U00 and U01 approximates the target unitary V on the system qubit. That's the intuition of our second cost function. For the first cost function, it has more parameters to optimize because W is also a parameterized unitary. But for the second cost function, this summation is outside of this absolute square. So actually we need more matrix multiplication compared with the first one. But an important thing is that here this UI0, the dimension of it is significantly smaller than the big U dimension of this big U operator. So in this sense, we prefer this second cost function because of the smaller matrix size. The good thing for the first cost function is that when we obtain this the optimized parameters, we can directly know about this W operator. So in this way, we can check the ancillar measurement output directly based on this cost function. So in general, this one is more preferable, but both of them work. So now here I will show some results. First, we want to use our protocol to prepare the long range gate. First, we prepare the long-range specific gate, which is C0, CZ, RZZ, etc. And this figure shows the result, shows the circuit structure to prepare this long-range specific 2-qubit gate. The circuit depth is constant depth 2, and the number of C0s is n-1. And then we want to prepare a long-range generic 2-qubit gate. This is the circuit structure. We can see now the circuit depth is constant depth 6, and the number of CNOTs is n-1 times 3. If we use unitary circuits to prepare these long-range gates, the circuit depth scales ON instead of O1 here, and the number of CNOTs also scale ON. We can see that dynamic circuits can reduce the circuit depth significantly compared with the unitary circuits. You might want to ask that what is the exact number of CNOT gates if we want to prepare the long-range gates. Here is an example of prepare the long-range CNOT gates. Y-axis is number of CNOT gates and x-axis is number of ancillas. We can see dynamic circuits also achieves less number of CNOT gates compared with the unitary circuits. So in general, dynamic circuits can prepare the long-range gates with shorter circuit depth and less number of CNOTs. Another application of dynamic circuit is for lattice simulation. Suppose we want to simulate the time evolution of TFIM on hexagonal lattice. This is the Hamiltonian of TFIM, and the hexagonal lattice is this structure if we only include the nodes in red color. Now we want to map the Trotter circuit of this time evolution to IBM's heavy hexagonal lattice. So here is the architecture of heavy hexagonal lattice. This is our Trotter circuit. If we use unitary circuit to prepare this Trotter circuit, this is the best we can get. If we use dynamic circuit to do that, we can also get a constant depth circuit shown here. Here are some results. The x-axis is number of qubits for this lattice simulation circuits, and y-axis is number of CNOTs, where we want to map the circuit to this heavy hexagonal lattice structure. We can see dynamic circuits always achieve the least number of CNOT gates compared with the other unitary methods. So this base case 0 RZZ means this best unitary circuit that we can get. We can also just map the circuit on this hexagonal lattice directly use Qiskit transpiler with optimization level 3. And in that way, the circuit depth, we need much larger number of CNOTs compared with this unitary circuit. And also in terms of circuit depth, we have constant depth 4, and then for the unitary circuits, we can obtain either constant depth 7, or if we just map the circuits directly using Qiskit transpiler, the circuit depth increases as the number of qubits. So in this application, dynamic circuits also reduces number of CNOT gates and circuit depth. Now I want to show some hardware results of long-range gates. Before we see the hardware results, we need to take a look at the hardware characteristics. We can see the measurement error is around 10 times more than the 2-qubit gate error, and also the duration is 20 times longer than the 2-qubit gate duration. For the feed-forward loop, it's also like 10 times as long as 2-qubit gate duration. So based on these hardware characteristics, let's take a look at the hardware results. Just to recap, the dynamic circuits can prepare the long-range gates with less number of CNOTs and shorter circuit depth compared with unitary circuits. But the hardware results show that the unitary circuits perform better than the hardware results in terms of the fidelity. It is because of the high error of measurement and also the long duration of measurement and feed-forward loop. If it has long duration, it will introduce more decoherence error to the circuit, which can decrease the circuit fidelity. So now we want to ask, so we can see that to make dynamic circuit better outperform this unitary circuit, we must improve the fidelity of mid-circuit measurement. Now we want to ask, to what extent do we need to improve this mid-circuit measurement fidelity such that the dynamic circuit can outperform the unitary circuit? So here is a fidelity projection analysis. We first propose a fidelity model that can predict the output fidelity given a quantum circuit. It includes the 2-qubit gates, single qubit gates, and mid-circuit measurement. This N is the total number of qubits, and M is the mid-circuit measurement cycles. We assume that mid-circuit measurement always have negative impact on all the other qubits. So this is a worst-case scenario. And this part shows the coherence time of the qubit. So now we want to find the MCM fidelity such that F unitary is equal to F dynamic circuit. Here is the results for state preparation, and this is result for unitary preparation. For state preparation, we have GHZ state and W state. We can see because for GHZ state, the improvement in terms of circuit depth is not very significant. So we really require a very high MCM fidelity. I forgot to mention that this dashed line is the current readout fidelity of AQT quantum hardware. We set it as a baseline to see how much it needs to be improved. But for W states, as the improvement of circuit depth is more significant, so as we increase the number of qubits, the MCM fidelity required is decreased. And this is for the analysis for unitary preparation. We can see for this long-range CNOT gate and arbitrary 2-qubit gates, as we increase the number of qubits, the required MCM fidelity is dropped significantly because the dynamic circuits has a significant advantage in preparing these long-range gates. This is the results for this lattice simulation. It also requires a pretty high MCM fidelity because both unitary circuit and dynamic circuit can prepare the target circuit in constant depth. The improvement of dynamic circuit is not as significant as this long-range CNOT gate and arbitrary 2-qubit gates. Also, this one is a worst-case scenario. The other thing I want to mention is that this fidelity model, it really depends on which quantum hardware that you use. If you use maybe trapped ion quantum hardware, this figure will be significantly different from the one that we use here, because the target is superconducting quantum hardware. So now I will introduce the customized circuit structure and ancilla count. As I mentioned before, when I tried to explain our protocol, I fixed the number of ancillas to one ancilla, but we can extend the number of ancillas to arbitrary count. So now, just for illustration, we have 2 ancilla qubits. We propose this customized circuit structure, and for each structure, we can simply update our cost function, and it will work for all the cases. The first one is the simultaneous measurement. We measure these 2 qubits simultaneously. We obtain 4 branch circuits, and this is the big U. This is the way we represent the big U operator. We can also measure these 2 qubits independently. So we measure A1 first, we apply U0 and U1 to all the unmeasured qubits. Then we apply some unitaries, and then we measure A1 and apply the conditional unitary to the system qubits. The third one is asymmetric nested measurement. Again, we first measure A1, then we measure A0 only if the measurement result of A1 is equal to 1. And then we have 2 other branch circuits. The fourth one is symmetric nested measurement. So first we measure A1, and then no matter what measurement results we get, we measure A0, and then we obtain other 4 branch circuits. Our cost function can be easily adapted to all this customized circuit structure. So to conclude, we propose a framework that can generate arbitrary dynamic circuits for arbitrary states and unitary operators. And our dynamic circuits can reduce the circuit depth and sometimes reduce number of CNOTs, but based on this based on the hardware results, we can see that we really need to improve the fidelity of mid-circuit measurement to bring the benefits to dynamic circuits. As we are moving to fault-tolerant regime, we have to improve the fidelity of mid-circuit measurement. So we will regard this mid-circuit measurement protocol as a bridge between NISQ and error-corrected quantum hardware. For future works, first we want to update the search step of synthesis for the branch circuits, because for all the results I showed before, the branch circuit is limited to 1 layer of U3 gates. We can make the branch circuit to have more complicated circuit structure. And the second future work we want to do is that we want to adapt the partition method to Biscuit to handle the dynamic circuits, such that we can scale up the dynamic circuit method to much larger circuits, like 100 or 1000 qubit circuit. Also, we think this dynamic circuit has the potential to facilitate the discovery of new methods for magic state injection and distillation. You can find our paper here in archive. And so that's all for the first part of the presentation. I will pause a little bit if anyone has any questions on this part.
Okay, great. Thank you for this part. Let's check our chat first. And in the meanwhile, if anyone has any questions, please raise your hand. I can see that there was a question from Greg related to one of the earlier slides. Why is the noise higher on W5 and W6 in the noise simulation?
Wait, let me go back. I think here this higher TVD, higher TVD means that the noise is the higher TVD, the worse is the fidelity results. So actually, this for W5 and W6, the dynamic circuit achieves better fidelity results compared with the unitary circuits. It is because this W5 and W6, I didn't show the complete results here. You can find it in the paper, the number of CNOTs, and the circuit depth first is reduced compared with the unitary circuits. And I believe this number of CNOT gates is also approximately similar as the unitary circuits. Based on this reduction in the circuit depth, I believe that's the reason that why dynamic circuits have better results compared with unitary circuits.
Okay, thank you. All right. I do not see more questions on the chat now. So Greg, I hope that it answered your question. Maybe someone would like to ask something. If so, please raise your hand. If not, then I think we can go on to the next part.
Sounds great. So,
sorry, there is just one new question on the chat. The question from Dev. Which hardware platform is providing the facilities of dynamic circuit, mid-circuit measurement at the same time?
and as far as I know, I think IBM for sure they provides that since we evaluate our methods on IBM, and then Continuum also has this feature. I think INQ also has this feature.
All right.
Yes, and this neutral atom device, I remember they also post some papers that also use mid-circuit measurement.
Okay, thank you. All right. Let's maybe wait a few seconds. Perhaps someone would like to ask something else. Okay, I think we can go on to the next part.
Sounds great. So for the second part, I will introduce our recent work on performance analysis of observable estimation in quantum simulation. Again, before I start, I want to acknowledge all my collaborators from different universities, national labs, and quantum companies. First, let me briefly introduce quantum simulation. Why are we interested in quantum simulation? We can see there is a very famous quote from Richard Feynman. He said, nature isn't classical. If you want to make a simulation of nature, you'd better make it quantum mechanical. So if we want to simulate a quantum system, it's very natural for us to simulate it use a quantum computer. So that's the reason that we are interested in quantum simulation. It is believed as one of the most potential quantum applications that can demonstrate quantum advantage. So for this Hamiltonian operator H, it can determine a quantum system's energy and evolution. To do quantum simulation, there are two main applications. One is quantum dynamic simulation to calculate this e to the power of ITH. One method is to use first-order traumatization. The second application is the ground state energy estimation, try to minimize the expectation value of the Hamiltonian. One algorithm to solve it is to use variational quantum eigensolver. The Hamiltonian can be mapped to qubits. So it can be represented by the summation of these weighted Pauli strings. C is some weights, some coefficients, and this P is the Pauli string. And our focus of this paper is to calculate the energy of the Hamiltonian. We also call it expectation value. It is equal to calculate this equation. Because H is equal to the summation of this weighted Pauli operator, we can expand this equation to the summation of this Ci and this Pi here in the middle.
Okay, Siwan, there was one question on the chat. Could you please recall the title of the second presentation of this part, if there is?
Yeah.
Preference analysis of observable. Good. Thanks. Thank you. Yeah, we can go on.
No problem. And in our work, we proposed a framework for quantum simulation in terms of the observable estimation. And our proposed framework is embedded in QUDC application-oriented performance benchmark framework. I will explain the details of this benchmarking framework in the next slide. So this is the structure of our proposed framework. First, we import some condensed matter and chemistry models from HAMLib. HAMLib is a Hamiltonian library, which I will also explain later. And then we obtain a bunch of Hamiltonians. Then we generate answer circuit for this Hamiltonian. We also evaluate some optimization techniques for quantum simulation. We combine these optimized methods and answer circuit together, and then we run them on either simulator or quantum hardware. I will explain each block in the following slides. First one is the QUDC benchmarking framework. It is an open source framework for benchmarking quantum applications on different quantum platforms. This is the architecture. It includes a bunch of quantum algorithms that we're interested in, such as Fourier transformation, confidence estimation, QAOA, VQE, etc. And then we can pass this algorithms to the execution managers. For the gate model-based systems, we can use like Qiskit, CUDA-Q, Circ, etc. to compile the quantum circuits, and then it passed to the gate model-based systems like superconducting or trapped ion quantum computer to run the circuits. Also, we have some benchmarks for this annealing systems. We pass it to this an execution manager, for example, the ocean, and then we can run on annealing systems like D-Wave. After that, we can pass the hardware results back to the QUDC framework. It has the metric collection and functions for metric collection and analysis that can analyze our hardware results. And all the results are stored in a data file. And then the QUDC also has some plot generation functions that can help us visualize these hardware results. Our proposed framework is embedded in this QUDC benchmarking framework. Then let me introduce HAMLib. It is a library of Hamiltonians with problem size ranging from 2 to 1,000 qubits. This HAMLib includes lots of problems spanning chemistry, physics model, discrete optimization, and binary optimization and related problems. All the good things that all of these problems have already been mapped to qubits. By that, I mean we can obtain the Hamiltonian written in this format. We select Hamiltonians from HAMLib, and then we construct the circuits for the Hamiltonian, and then we benchmark their performances. Since our focus is on observable calculation, now let me introduce some common calculation methods. The first one is we can just use classical matrix multiplication to calculate this observable, but it only works for small systems because the dimension grows exponentially as the system size. We can also use Qiskit estimator to calculate the observable. This is the syntax for that. This is the circuit, and this is the observable we want to calculate. If the circuit is a parameterized circuit, we can give the parameters theta for this parameterized circuit. And then after we run it using simulator, we obtain this expectation value of the observable. The third one is to use CUDA quantum spin operator. The spin operator itself doesn't allow us to do the observable calculation, but we can represent the Hamiltonian using the spin operator and pass it to CUDA quantum kernel for GPU accelerated simulation. Just to recap, this is our proposed framework. We obtain the models from HAMLib, which is written in this format, and then we just use the answer circuit and we evaluate these optimization techniques, including k-commuting, Clifford measurement, and circuit generation, and weight shot distribution method. And then we combine them together and run on the simulator and quantum hardware. Now I will introduce different optimization technique. The first one is about commuting Pauli groups. So if we want to calculate the energy of the Hamiltonian, we have this Hamiltonian is composed of a bunch of Pauli strings, of different Pauli strings. And since we can only measure the circuit on Z basis, if the Pauli string has some X or Y term, we need to generate a measurement circuit to convert this Pauli string to the Z basis such that we can measure them and calculate the expectation value of this Pauli string. In that sense, we need to execute L circuits to calculate this expectation value of this Hamiltonian, which is a large overhead. But luckily, according to some theory, it shows that for any mutually commuting Pauli strings, this P alpha is some commuting Pauli strings, there exists a Clifford unitary U such that U P alpha U dagger is diagonal for every alpha. It means that we can just measure this group of Pauli strings simultaneously using this Clifford unitary U. It can reduce the number of circuits, but now we need to think about how do we implement this Clifford unitary U. In the literature, for the commuting method, people are focused on this qubit-wise commuting and fully commuting method. For example, for qubit-wise commuting, here's an example. We have xizi and iyiz. Each qubit commute with each other, which means X commute with I commute with Y, so forth, so on and so forth. So in this case, we can see if we have a bunch of Pauli strings and we want to find the groups that satisfy this qubit-wise commuting, it is a pretty strict rule. The number of circuits will be pretty high if we follow this qubit-wide commuting. But the good thing is that the measurement circuit depth is very short. It only scales 0.1. The other commuting method is fully commuting. So this one is example. We have XXYZ and YYZI. They are not qubit-wise commuting, but they are fully commuting. For this kind of method, we require, because this requirement is much looser than the qubit-wise commuting, so we require less number of circuits, but the measurement circuit depth scales O(n) squared over log n. Because this rule is not as strict as this qubit-wise commuting. If it's qubit-wise commuting, it must be fully commuting, but if it's fully commuting, it doesn't mean that it's qubit-wise commuting. To reduce the general overhead, we want to reduce the number of CNOS. Also, we do not want to have a very large circuit depth for the measurement circuit. So it motivates us to ask the question, is there a way to balance the number of circuits and the measurement circuit depth? It introduced the first optimization technique called k-commuting group, which is first introduced in this paper. So what is k-commuting? So for two n-qubit Pauli strings P and Q, we can divide this Pauli string to a bunch of blocks, and each block has k qubits. If each block from P and Q, they commute with each other, we say that P and Q are k-commuting. Here is an example. We have a group XXII, YYZZ, and ZZXX. They are two qubit commuting because we have two blocks here. The first block is XXYY and ZZ. They commute with each other. The second one is IIZZ and XX. They also commute with each other. So we call it two commuting group. To diagonalize all these Pauli strings, first we can construct a unitary U to diagonalize the first part, and then we have another matrix, unitary matrix V to diagonalize the second part. Then we have U tensors V that can diagonalize all the Pauli strings. So why this is interesting? So we can find the answer from this figure. This is the results for a very large Hamiltonian. The x-axis is the value of k and y-axis is number of groups. We can see as we increase the value of k, the number of groups will be dropped significantly at the beginning, but after a certain point, it will saturate. So this sweet spot is the one that we want, because in that sense, we can achieve the smallest number of groups, the same number of groups as we do for Pauli commuting group, but also the measurement circuit depth is smaller than the Pauli commuting group. And also this metric R shows the precision of the can represent the precision of the observable estimation. We can see there is some correlations between the precision and the value of key. If we increase the value of key, the precision is also improved and then saturates. That's why we are interested in these key commuting groups. So now we know how we proposed a method to do this key commuting groups, and you can find the more details from this, from our paper's description. No, it's not we proposed, it's they proposed this key commuting group. We try to evaluate their method. You can check this paper for more details. And now we have this method to construct these key commuting groups. But what lacks in this paper is that it doesn't propose a method to construct the circuit that can diagonalize these key commuting groups. So in our paper, we proposed an algorithm that can do this diagonalization. Here is an example to explain our method. For example, we have a Pauli commuting group of 3 qubit Pauli strings, of 3 Pauli strings, and which is P1, P2, and P3. First, we will pick the left minimum qubit index such that the Pauli operator is not equal to identity. If we start from index 0, here for P1, the left minimum qubit index is 1 because X is not equal to identity. For P2, the index is 0 because we have Z here, and the same for P3, the index is 0. We randomly pick P2. So we first want to diagonalize P2. We want to transform P2 to ZIZZ to make it diagonal. To do this, because it has an X operator here, we need to transform X to Z by adding Hadamard gate. If it has a Y operator, we need to add X and Hadamard gate to transform it to Z basis. So we can see for here we add a Hadamard gate to Q3 here. The third step is that we need to transform ZIZZ to ZIII using some C0 gate. The reason we want to keep it as identity is because we first make this diagonal, but we also need to handle all the other Pauli strings. If we keep this P2 as I and Z, when we add some other Clifford operators, it will further change this Z operator to some other basis. So in the end, we cannot diagonalize this one. We make it to ZIII such that if we add other unitary operators, it will not influence this I operator. That's why we want to keep it to identity here. We repeat this process until all the Pauli strings are diagonal. So this is the part we diagonalize P2, and then this is for P3, and this is for P1. Now this circuit can simultaneously diagonalize these 3 Pauli strings. In our paper, we also proposed another method, which is the weighted shot distribution. So here we can see this is the Hamiltonian of H2 molecule. It is composed of a bunch of Pauli strings. Let's take a look at the coefficients. We can see these coefficients are significantly different with each other. The largest one is like 100 times larger than the smallest coefficients. According to this theory when we calculate the expectation value of this Hamiltonian, we need to value more of the Pauli terms that has the larger coefficients to make the observable calculation has higher precision. So let's say given a fixed shot budget, we need to allocate more shots to the higher weighted terms to get higher precision. But usually people do is that they just distribute the shots, they just uniformly distribute the shots to all the Pauli to all the groups. So now we propose that we can distribute the shots to these n commuting groups according to the weights of the Pauli terms within each group. But this causes another problem. If we distribute the shots equally to all the n commuting groups, we can just put this n circuits to one job and submit this one job to the, for example, IBM quantum hardware. But if we distribute the shots in a non-uniform way, we need to send the n jobs to the cloud instead of one job. It will increase the time we need to wait in the queue for these jobs to be executed. To tackle this issue, we proposed a method to bin the circuits with similar shot counts to key execution groups, where k is smaller than n. In this way, we can only submit, for example, submit k jobs to the cloud. It can be seen as a trade-off between this weight shot distribution methods and also the number of jobs that we want to submit. In this way, we can use less number of shots, which directly means less execution time on the quantum hardware with high precision on this observable estimation. So now I want to show some experimental results. So for the first evaluation, we want to check the impact of Pauli string grouping method and weighted shot distribution on the observable estimation. We just fix the trolley step to 0 to eliminate trolley error because we only care about these methods. We prepare the Hamiltonian with random initial states and repeat the experiments for 100 times. These are the benchmarks that we obtained from HamLib. The first 4 are condensed matter physics models, and the last 4 are some chemical systems. We fix the number of qubits to 12, and this is the number of terms in the Hamiltonian. In terms of metric, we use error between the simulated and theoretical energies. This error is quantified as the standard deviation of differences between the simulated results, which we obtain using Qiskit Air simulator, and the theoretical energies, which we obtain using NumPy across these multiple runs, which is the 100 runs. So here we first show the impact of grouping methods. We choose k equal to 1 n over 4 n over 2, 3n over 4, and n, where n is equal to 12 in this case. The x-axis is the Hamiltonians, y-axis is number of groups. We can see for these chemical systems, as we increase the value of k, the number of groups is reduced. But for these physics systems, the results is a little bit unstable. It is because the grouping method is actually greedy. Every time when we have a new Pauli string, we just allocate to an existing groups or a new group. There is no guarantee that we always obtain the optimal or the smallest number of groups. That's why there are some fluctuation here. But in general, overall, the number of groups decrease as we increase k. Here is the results of the impact of this grouping methods on the errors for observable estimation. We can see when we increase the value of k, the errors is decreased. On average, the error is reduced by 27% compared to the qubit-wise commuting method, which is 1 here, which is represented by 1 here, qubit-wise commuting method. Here is the impact of weighted shot distribution methods. First, we try to fix the number of shots to 4,000. Again, x-axis are the different Hamiltonian, and y is the errors of the observable estimation. We use this fully commuting grouping method because now the variable becomes this weighted shot distribution. First, we just allocate the shots in a uniform distribution, and which is represented by n. Here we set it as a baseline. Then we use different methods for this weighted shot distribution. So we use the mean value of the coefficients or the maximum or the square of the mean or the square of the maximum value. And here are the results. We can see the mean weight distribution method performs the best among all these methods. Overall, it improve the errors. It reduces the errors by 37% compared with the uniform distribution. So here's another experiment. Now we do not fix the number of shots. We try to vary it from 1,000 to 8,500. And then we want to evaluate what's the errors if we give the different number of shots to different number of shots. We can see we use this n is the uniform distribution and this is weighted shot distribution. And then this is the shots from 1,000 to 8,500. We can see if we have more shots, then the errors will be reduced. That's the general trend. But let's take a look at this example. Assuming a baseline of 8,500 shots and a uniform distribution, which is this one. If we go back and we can see that when we use this weighted shot distribution method, we can only use around like 1,000 shots to achieve the similar errors compared with the uniform distribution. That's a big advantage of our weight distribution method. Overall, it reduced the number of shots by over 50%, which directly translates to a 2.6 times speed up in evaluation time. We also have another evaluation focused on the circuit execution time. For this evaluation, we just perform end-to-end simulation by setting one total step of Hamiltonian simulation with a fixed initial state. We choose the grouping method k equal to 1 and k equal to n. We run the circuits on bunch of platforms, including IBM Quantum hardware and different simulators, the ideal air simulator, noisy simulator, and produce unveil cluster using NVIDIA GPU. So for this method, we use spin operator to represent our Hamiltonian and use this GPU to use NVIDIA's GPU to speed up this simulation process. First, we report the execution time of this TFIM simulation. The number of qubits range from 4 to 42. For air simulator, we use 10,000 shots for ideal simulation and 2,500 shots for noisy simulation because noisy simulation is very slow compared with ideal simulation. We can see the x-axis is number of qubits, y-axis is the execution time. These two lines shows the results when we use the noisy simulator with k equal to 1 and k equal to n. We can see there is a gap between them. This k equal to n can reduce the execution time by 4 times compared with k equal to 1. And this line is the results for this GPU simulation. It requires the least amount of time compared with other simulators. And these are the results for the hardware execution time. We can see it is kind of stable. It does not grow like exponentially like this as we increase the circuit size. Here we also want to show some result quality of this TFIM simulation. For this noiseless 1Q and NQ deviations, because these are the 1Q and NQ deviation compared with this exact value, there is some deviation. It is because of the Trotter error, because we only set Trotter step 1. For this noisy 1Q and NQ deviation, this is noisy one, and this is the noiseless one. Sorry for the mistake. This is not this one. It is not exactly the same as the exact value because of the trolley error. This is the noisy one, and the deviation is larger because it contains not only trolley error, but also these noisy operations. For this GPU simulation, is this line. There is only trolley error, but the deviation is smaller than error simulator. It means that this spin operator, this or CUDA quantum, they do some optimizations here to reduce this error. And these are the results for IBM quantum hardware. We can see it diverge from exact value when the qubits is more than 12. Here, the results is not very good because one reason is because we do not add any error mitigation methods. When we add it, we would assume the line will get closer to the exact value. The other, so also we need to remember that hardware has lots of errors, and so it's for now it's also very normal that for large circuit executions we do not get very promising results. Another reason to explain these bad results can be the limited shot count, because for large systems, usually we need to allocate more shots, but here we just fix the number of shots. So that might also be a reason why the results is not that good. So to conclude, the k-commuting group and weighted shot distribution can reduce the execution time and also improve the precision of the observable estimation. The previous results of GPU simulator demonstrate these fast and accurate simulations for the large-scale systems. Our framework can allow users to explore their applications and investigate new algorithmic optimization techniques. And also our code is available here. Feel free to check. Also, I want to advertise that this work is accepted and will be presented in more details at IEEE Quantum Week in Albuquerque at the end of August. So if you are also there, please join, and you can also check our paper here. That's it for my presentation. Thanks for your attention. And also I want to advertise that I'm hiring motivated PhD students and postdocs. If you're interested, feel free to email me your CV. Thanks for your attention.
Great, thank you. Thanks for the presentation. All right, congratulations. Okay, it's time for questions. So let's see. I do not see more questions now on the chat, but maybe someone would like to unmute and ask a question. Let's wait for a while. Helen, do we maybe have some questions on YouTube? Can you check?
So far, I don't see any question on YouTube.
Okay.
They just say thank you so much.
All right. Okay, I do not see questions here either. So, Helen, I think we can maybe just finish a bit earlier today. What do you think? There are no questions.
Sure. So,
Mhm.
do
There were some,
anybody have question?
yeah, there were
Please.
some questions about sharing the slides. So maybe we can also ask Yuan already if it's fine for you to share your slides later with Helen, and she could distribute the slides
Yes.
to the participants.
Sure. I'll ask Dr. Liu for the slide and I can share. And I got a feedback. I really like your work, Dr. Liu. Thank you so much.
Send the slides out. That's always good.
Okay.
Deserve closer study.
Yes, there is a question about the. Yeah, we have Siwan with us once again. Yeah, so we just said that we do not see any questions here on the chat or on YouTube. So in this case, we'll probably just finish a bit earlier today. There was just a question about your slides. If you could share your slides with the participants. Yes, okay. So you can share them with Helen, and Helen can distribute the slides to the participants. Good.
I just noticed a question from Dr. Dev. He
Yes.
said, is this code free of cost for all? Excellent presentation.
Can you repeat the question?
So there was a question about the code. So
The code is the code free of charge?
Terry shared a link to the code on GitHub, and there was a question whether people can use this code for free.
Yeah, it
Yeah.
is free.
Okay, thanks. Okay, so Helen, I think we can finish for today then. So thank you, Dr.Niu, once again for a great presentation.
Thank you.
Thank you.
Thanks. And we hope to see all of you next time on our next meetups. Thank you.
Thank you. Bye.
Bye-bye. Have a good week.